Let's go. Okay, so where did we leave off last time? We did the Cauchy representation formula, right? Cauchy Integral Representation, which was that if F from some open set which contains a closed disk is holomorphic, then for all z in the disk, if you take 1 over 2 pi I, the integral over the circle, which is the boundary of the disk, you take the circle as usual, counterclockwise oriented, f of w minus z dw, you will recover f of z. Okay, you integrate over a circle, you have some region omega, whatever it is, you have a disk inside omega, and you have a point z, not necessarily at the center, just anywhere, and you integrate the values of f over the disk. F is only being sampled on the disk, but this function, it's kind of like saying the universality of the function w minus a fixed point, that this function will pick off the value of any function integrated over any disk that contains this point. Okay? We remember this, right? We did this last time? Yes, no, maybe? Yes, okay. And then we did derive, if I remember, and then we derived a corollary. So theorem. In fact, you can get the nth order derivatives as n factorial over 2 pi I, the same integral, the same f, not derivatives of f, the same f, but over the function w minus z to the n plus 1. This we also finished the proof of. Is that right? Yeah. So this is for all n. And in particular, this means, i.e., if you are holomorphic, if you have one derivative, then you have infinitely many derivatives, because here they are. And that's how we computed the derivatives. So once differentiable means infinitely differentiable, and we have a formula for the derivative. This is where we left off. Is that accurate? Great. There's some amazing consequences. We're about to get to the fireworks. So here's an easy corollary. These are called the Cauchy bounds, Cauchy inequalities, Cauchy inequalities. So all we're going to do is put absolute values in. So again, if f is, and this contains a disk, the closure of a disk, is holomorphic, then, and let's say the disk is a ball of radius r about a point z0. I mean, not the closure of the disk. Okay, balls for me are open balls. So let me close both of them if I'm writing it like this. Then we can bound the value of f at the center. And let's see what we can bound it by. So here's the proof before we know what just a calculation. So you take this formula, with n equals 0, just the value of, so we have f of z0 is equal to 1 over 2 pi I, the integral over c of f of w over w minus z dw. That's just the Cauchy integral representation form. I take absolute values. I bring those absolute values inside. Let me pull out the worst value of f. So this is the supremum of absolute value of f on the circle, on the boundary of the disk. Whatever the worst value of that is, I pull out. And then I get 1 over 2 pi I, 1 over 2 pi, the absolute value of I is 1, and then the integral over the circle of 1 over r, because the absolute value of w minus z is r. Z is z0. I'm at the center of the circle now. dw. Well, that's of course just the length. And the circle has length.
Two pi r.
What is it?
2 pi r.
2 pi r. All right, so what do we see? We see, first of all, that the value of a point, this is sometimes called the maximum modulus principle, the value of a point in the interior, okay, so this 2 pi r, the point is this 2 pi r cancels off this 1 over 2 pi r. And so the whole thing is bounded by the supremum of f on the circle. We're going to get to the maximum modulus principle in a second. So what this means is the value at the center of a disk cannot be larger than the value on the boundary. And in fact, that's going to be true for any point in the interior, but we're going to get to that in a second. But it hasn't given us very much information yet. Let's look at what this might say for derivatives. So I'm not done with the proof yet because we're going to get more information out of it. What if we took the nth derivative of f? So again, the formula is n factorial over 2 pi I, integral over the circle, the value of f over w minus z0 to the n plus 1. Right? That's the Cauchy integral representation for the derivatives in terms of the function itself. Take a minute and work out for yourself what an upper bound for this would be, and give me a thumbs up when you have one. Rishab's got it. Mitchell, do you have a bound?
I'm still thinking.
Okay. Sriram's got it. Nick? Burchin, you got it? What'd you get?
It is bounded by n factorial over r to the n and supremum of f.
Beautiful. So let's do it a little bit more slowly. This has absolute value r to the n plus 1, r to the n plus 1, and there's a 2 pi I in the denominator. Let's see. Can I connect this to this? And then let's put a 2 pi I, 2 pi in absolute value. And then the length of the circle is, of course, 2 pi r. So that cancels the 2 pi and one of the r's. So what we have proved is that for all n, the nth derivative is bounded by n factorial over r to the n times the supremum of the absolute value of f on the boundary. Everybody see that? Okay. Now, what we can do is we can prove the theorem, the main theorem that we've been headed for. if I can still see. I sort of have it here. So here's this is a watershed moment, because what we can show is that a function, so theorem, we already know that if it's analytic, if it has a convergent power series, then it's holomorphic. Now we have if and only if. And so what do I mean by this? What do I mean by this? If F is holomorphic, excuse me, this is always open. I always want to take an open domain on which I have F. So there exists, so for all Z in omega, there exists some, the definition of open is there's some ball around your point. There exists some D in omega that contains Z. In fact, contains it at its center. So that Z is so the D is equal to a ball of some radius about Z. And I want to give myself just a little bit of room so that I can take the integral on the boundary where originally the function may not be defined. You see what I mean by this? I'm going to want to take the integral over the bounding circle. But if I let D, you see, if omega looks like this and I let D be this circle, then I might not be able to take F on the boundary. So just take a slightly smaller disk and then you can integrate F on the boundary, no problem. I don't want the boundary of D to interact with the boundary of omega. Okay, so that's what this overline is doing here. Okay, so if it's holomorphic, then it's analytic. In other words, if F is open, then for every Z, there is some positive radius ball, so R is positive, such that F of Z is given by a power series for all Z0. Let's call this point Z0. For every point Z0, such that for all Z in the ball of radius R about Z0, we have a power series representation. And what are the ANs? They're the same as they were in Calc 2. Right? This is just Taylor's theorem. So what are they?
F, the nth derivative at z naught over n factorial.
Yeah. Okay, how do we prove this? How do we prove this? Proof. Okay, we have the integral representation. By integral representation, we know that F of Z, so for all Z in this disk, well, the disk is a ball of radius R about Z0. We know that for all such Z, F of Z is 1 over 2 pi I integral F of W, F of W over the circle divided by W minus Z. EW. But I want to somehow, what I want, if I want to see these derivatives, if I want to see these nth derivatives at Z0, what I want is something that has a Z0 here in place of Z. Want W minus Z to be replaced by W minus Z0 so that I can start reading off derivatives at Z0. The problem is that's not what I have here. So here's the idea. Solve this equation. One where I have 1 over W minus Z, I want it to be 1 over W minus Z0 times something. And it turns out it'll be convenient to break that something into a power series. So into a geometric series. Okay, this is the key idea. Take what I have, turn it into what I want with, of course, they're not equal. I have to put something else there. So we're going to solve for x. Okay, so solve for x. So this is very simple. The geometric series converges to altogether
1
Yeah.
over 1
1
minus
minus x.
right. Now this is only if absolute value of x is less than 1. So we have to check that. But let's solve it anyway. All right, 1 over w minus z is supposed to be 1 over w minus z0 times 1 over 1 minus x. So the 1 overs we can cancel. And 1 minus x is supposed to be w minus z over w minus z0. And so x is supposed to be 1 minus w minus z over w minus z0. And that's a w minus z0 minus w minus z over w minus z0. Also known as, let's see, the w's cancel. And I have a z minus z0 over w minus z0. Take a second and verify that algebra. It's very simple. Is this true?
Yes, because the z is in like the interior of this disk. And then w is on the boundary. So.
Perfect.
Yeah.
Perfect. Let's remember where we were. We were on a ball of radius r about z0. z0 is at the center, z is somewhere else, and w is all the way out here. So this distance, by definition, is larger than this distance. And so in absolute value, x, not only is it less than 1, it's less than some r less than 1, uniformly for z less than, uniformly for z minus z0 less than what? R times little r or something. So if I give myself a slightly smaller radius, then I don't care what z was. This is uniform in z. Okay? Great. So we know what x is. So in other words, we're going to write 1 over w minus z, let's leave a little room, is equal to 1 over w minus z0 times 1 plus x z minus z0 over w minus z0 plus x squared z minus z0 squared over w minus z0 squared, and so on. And that series converges uniformly and absolutely. So now I multiply both sides by f of w. Now I divide both sides by 1 over 2 pi I. And now I integrate both sides over the circle dw. Everything is absolutely convergent. So I can interchange orders. What is this thing going to be?
Just f of z, right?
Just f of z. And what's all this stuff? The first term?
f of z0.
F of z0. How about this with an extra factor of this? There's a z minus z0 which pulls out of the integral. And what's left?
Z minus Z0 F,
F
prime
prime
of
of Z.
Z naught.
Yeah, because there's a w minus z0 squared. So it's f prime of z0. And how about the next thing? There's a z minus z0 squared. There's a w minus z0 cubed in the denominator, but we're missing a 2 factorial. So we're off by 2 factorial from what would be the second derivative. And so on and so forth. This is exactly picking off, this power series, this geometric series, is exactly the thing that picks off the nth derivative at z0 times the appropriate power of z minus z0. Anna, you like it? So F is given by a convergent power series at every point. Therefore, it's analytic with a positive radius of convergence. That's exactly what we wanted to prove up here. And it's just as simple as we had 1 over w minus z. We needed to replace it by w minus z0. The cost of that is a series. That series exactly converts the integrals into derivatives by the Cauchy integral representation. Should we check what the radius of convergence is? I mean, we've proved that this converges for all z less than r, but what about Hadamard's formula? How does this compare to Hadamard? Compare to Hadamard. Remember what the radius of convergence, 1 over the radius, was like, what was it? If you have coefficients an?
The limb sup of the nth root.
Of the nth roots. And if we're supposed to have, if these an's are supposed to be the nth derivative at z0 divided by n factorial, what's that bounded by? Let's see, I wish there was a way to split screen. Is there a way to split screen? Does anybody know? Split screen. View? No. All right, I'll play around with that later. What I want to do is show you this again. So the nth derivative is bounded by n factorial times this supremum over r to the n.
So it just recovers this 1 over r.
So it just recovers 1 over r. So this is 1 over n factorial times what we just said was n factorial over r to the n times the sup of absolute value of f over the circle. So the n factorials cancel. If I take nth roots, so an to the 1 over n is bounded by 1 over r times the nth root of this supremum. This is just a constant, so this of course goes to anything, well, as long as f isn't identically 0, okay. Anything that's not 0 to the 1 over n goes to 1. And so the radius of convergence of the function, I should write this, is the largest ball that you can take that's still inside the region omega. So whatever your omega is, whatever your point is, the largest r, radius r ball that you can take is exactly the radius of convergence of the power series centered at that point. For all z in omega, the radius of convergence is, well, I'm getting a little ahead of myself. We haven't gotten to analytic continuation. The radius of convergence could be bigger, and if it is, then your function could be defined on a larger region. The radius of convergence is at least the largest r such that the ball of radius r about z0 is still contained in your omega.
Can you explain how you got that?
Yeah. So I have this bound on the coefficients, and I have this bound on the radius.
Okay.
And this proof was take any ball of radius r about your fixed point.
Okay. Okay.
So what's the largest one I can take? It's basically a tautology. You get a radius convergence of the disk of whatever disk you could take around z0 and still be inside omega. Cool? Okay. All right. So holomorphic functions are analytic. And yeah, so here's an elementary corollary. So elementary corollary. If f is entire, we know what entire means. We've talked about entire before. It means holomorphic with the domain being the entire complex plane. Then f has convergent power series about 0 for all z. That's just a tautology. You start at 0. You can take a ball of any radius. And so any point, in other words, f of z, can be recovered by a sum of a n z to the n for all z in the complex numbers. The radius of convergence is infinite. It's arbitrarily large. Bertrand, did I lose you?
We're having a connection.
I have a bad connection?
All three of us.
Oh no.
She means she has a bad connection.
Oh, you have a bad connection.
No, we do.
Okay.
Kayla, Hannah.
Oh no. I don't know what to do.
I'm able to hear you fine.
Okay, so it's not on my end.
I don't think so.
Oh boy. Well, are you able to follow along? I see you put something in the chat. Okay, you can still hear me. Okay, good, good. All right. So if a function is entire, then it has a convergent power series about 0 at every point. This power series converges for every point in the complex plane. And so now we're going to get to some very striking corollaries. So this is Liouville's theorem. If f is entire and bounded on C, on all of C, then f is constant. The only entire functions are constant. This is a absolutely essential result, and yet its proof is absolutely trivial. What can we say about the first derivative of f using our Cauchy bounds?
It's like
N
this,
factorial over
yeah,
2
like soup
times the soup. Yep.
of f over
Over
1
some
over,
circle.
over r.
Yeah, let's take a circle of radius r times 1 over r, right? And I guess the 2 pi cancels the, it's really 1 over r squared times 2 pi r. So the 2 pi's cancel and one of the r's cancels on top and bottom. I'm reproving the theorem for you because I don't remember it, so, and I can't see it to quote it, so I have to reprove it. And this is true for any r, but the function is bounded universally, not just on that circle, not on any circle. The function does not reach higher than anything. True for all r. What can we say about the derivative? It's identically 0. And we already proved, or or I have to argue for you that if the derivative is 0, then the function is constant. We proved that way back.
We proved it.
We proved it way back. Good. Yeah, we constructed the primitive, and the primitive was a constant, right? On a simply connected on a connected region. Okay. In other words, if remember how we were graphing things, this was our complex plane, and here we would have sort of the absolute value of f of z, and then the color, the height was the absolute value. We saw things like this, and the color was the argument, and the color was arg f of z, right? So f of z can always be written as rho of z e to the I theta of z. So theta of z is the argument, and rho is the absolute value. I'm just writing things in polar coordinates. And so any function, there does not exist a complex analytic function that looks like this. That does whatever it does and then doesn't grow. If it doesn't grow at infinity and it's entire, then it's just the flat plane. This implies this. With a single color, with a single value, one value. Okay? Does that make sense? This is like, this is crazy. If you want to have an entire function, it's got to blow up at infinity. Somewhere. I don't know where, but it's got to blow up. It cannot stay bounded.
Does this mean that there are no non-trivial holomorphic functions on the Riemann sphere?
We're going to get to the, that's coming right up. The classification of functions that are meromorphic on the Riemann sphere. That's coming right up. They're the rational functions. I'll give it away. But we're going to prove that. We need a few more things before we can prove that. But there's something that we can prove immediately, which was something that people spent quite a lot of effort with various proofs of various levels of completeness. The fundamental theorem of algebra. Fundamental theorem of algebra. Which says if you have a polynomial, originally people were interested in polynomials with integer coefficients, and they wanted to know, do those always have solutions in, well, if not the reals, of do they have n, if the polynomial has degree n, does it have n roots? We already know that over the reals it doesn't. Quadratics don't have to have a root, or they could have one root. We count with multiplicity. But it turns out that you can just think about. So we're trying to produce a root. If f is a polynomial with coefficients that are complex numbers, then there exists a z in C such that f of z is 0. There exists a root. And in a second, we'll see why if there exists one root, then you can pull out that root just by polynomial division. Okay, so which implies f if f has degree n, then f has n roots in C with multiplicity. That's just polynomial division. We'll get to that in a second. Let's get one root. Let's get one root. So proof. Assume f, yeah. There's one thing that's wrong with my statement at the moment, and we'll fix it. We'll see immediately what's wrong. Assume f is a polynomial of degree n. Let's say the largest term is not 0. That's what it means to be a degree n polynomial. Assume f is a degree n polynomial, and f is never 0. On all of C. Of course, f is an entire polynomial. Then what? How do we get a contradiction out of this?
Consider 1 over f.
Then 1 over f. Then 1 over f. Since f was never 0, 1 over f is also entire. Now, what can we say about 1 over f? So 1 over f looks like 1 over an z to the n. So times something, well, it starts with a 1, and then it's some other number. B times b over z, let's say b1 over z, plus b2 over z squared, plus down to bn over z to the n, I guess. Where each bn is like each bk is ak over an. I'm not doing anything fancy. If z is larger than, let's say, all of the bi, I don't know, 10 times the max of the bi's, bk, then this series is a convergent series, and so 1 over f behaves like whatever, some constant over z to the n at infinity as z gets large in absolute value. Does everybody see that? In other words, all I'm saying is that all of these things are going to 0. In other words, well, but what does this thing look like? I mean, it's just decaying. It's exactly the kind of thing we just said doesn't exist. 1 over f is an entire function which goes to 0 as you go out. That means there's some compact region left over. In a compact region, well, it has some largest value. That means 1 over f is bounded. Which would mean that 1 over f is, we just proved Liouville's theorem, bounded entire functions are
Constant.
Okay, so other than Mitchell now, yes, are constant. And so f is constant. So there's one thing wrong with my statement of the fundamental theorem of algebra, which is that if f is not a constant function, constant functions don't have zeros unless the constant is 0. Okay. The constant is a polynomial of degree 0, and it has 0 roots. Okay?
Why is 1 over f bounded?
Why is 1 over f bounded? So there's some inside region where it takes whatever values it does, but it never blows up. And then outside of that region, it's going to 0. So there's some compact region where it can take whatever values it wants, but it's compact, so it's going to take a maximum.
Yeah.
And then outside of that, it's going to 0. Can't happen. Okay? I mean, you can really see this. Yeah. Maybe it's a good time to take a break. That's the fundamental theorem of algebra. We're going to come back and get more consequences in a minute. Okay, so those of you that were out, we just took some random polynomial and we plotted 1 over that polynomial in some range. And so it really does go to 0 out at infinity. The problem is it's not bounded. It has all these massive poles, and there's one more pole here that it's not sampling the heights of. And if you plot the function itself, then it's blowing up out at infinity, and then it has a couple of, these are the dots. These are where it hits 0. Although nearby it's pretty small, but it's, this is at a scale of 10,000. So it's, let's see, maybe I can make the scale a little better. All right, anyway, you get the point, right? We don't need to waste more time playing with this. Okay, back to theorems. So we proved that there's a single root, and then how do we know that we have n roots? I sort of said
By
it.
induction.
Yeah, by induction and polynomial long division. So once we have one root, f of z is equal to z minus whatever that root is times g of z. This is polynomial long division. And g has degree n minus 1. And then induct down to g equals constant, degree equals 0. Okay? So you just keep pulling out roots, and you can pull out any of them until you get to a constant function, and a constant function has no roots. So any polynomial has exactly n roots. And it's just one line. I mean, the one line is 1 over f is entire and bounded, therefore constant. But I sort of spelled out the details more than that. Okay, does that make sense? Okay. Now let's get to some analytic continuation, the beginnings of analytic continuation. So here's a fun theorem that we're going to get from analyticity more than holomorphicity. This is analytic continuation. The beginnings of analytic continuation. You'll see in a second why I'm calling it this. Continuation. If f is holomorphic, and really all I'm using is that it's analytic. But we proved that holomorphic implies analytic. And there exists a sequence zk, distinct values, converging to z, all in omega. Such that f at all of the zk is equal to 0. Then f is identically 0. In particular, so maybe you'd like to see a function, or non-example, maybe there's a function whose graph, maybe it hits 0 at 1 and a half and a quarter and an eighth and so on. It's very easy to make such a function in the real variables. You just kind of draw it, 1, a half, a quarter, no problem. Right? There's no problem drawing a function that does that. And it's infinitely differentiable and so on. Not analytic. Can't be a function. So there's no holomorphic function. No holomorphic function with a limit point of zeros. Okay, that's what. And again, it's not holomorphicity. It's the difference between smooth and analytic. So it's the convergent, it's having a power series that converges on a finite radius. So this is true just as well for real analytic all we use is convergent power series, with the positive radius of convergence, of course. Okay, so let's prove this. So say we have a sequence ck converging to z in omega. F is analytic at z. So there exists some disk containing z such that, so let's call this z0. It converges to z0. The zk converge to z0. Okay, these are the zk's, and they converge to some point which is z0, the limit point. So far, so good? F is analytic there. So for all z in that disk, f of z is equal to a sum an z minus z0 to the n. We have a convergent power series. If the function isn't identically zero, if f is not identically zero, then there exists a least n such that an is not zero. So it certainly does vanish, by the way, at z0. Why? Why must the function, we only assume that the function vanishes at zk, but in fact it must also vanish at z0.
By continuity, right?
Other than Mitchell, yes, but just because it's continuous, right? Note that n is at least 1 since f of z0 is 0 by continuity. All right, so there's the first couple of Taylor terms are 0, and then you get to your first non-zero Taylor term. If there is no non-zero Taylor term, the function is identically 0, that's what we want to prove. So if there's a first non-zero Taylor term, then, again, as we saw before, for all z close enough to z0, in other words, in that disk, f of z, let's call this at least capital N. Okay, so this capital N is at least 1. F of z is a capital N z minus z0 to the capital N times 1 plus something else, g of z. And this g of z goes to 0 as z goes to z0. It's all the higher order terms, right? It's a power series where we picked off the leading order term, and then there are lower order terms. So for z near z0, this 1 plus g of z, well, is at least a half, let's say. Because there's 1, and the g of z is going to 0. So if you're close enough, make g of z less than a half, so that 1, the smallest it can be is negative a half. 1 plus negative a half is a half. That's all I'm saying. Does that make sense? And now evaluate f of z at z equals zk with k large enough that zk large enough that zk is close enough to z0. So f of zk is some non-zero number times zk minus z0 to a power times 1 plus g of z. And what's wrong with that?
Not 0.
Exactly. What we said is f vanishes at all the zk's. So this thing is supposed to vanish. This thing is at least a half in absolute value. In other words, it doesn't equal 0. How about this? The zk's are all distinct, and they're distinct from z0. It's a true limit point. You're not just hitting z0 infinitely often. And how about that leading term? You have 3 non-zero things multiplying together to be 0. Oops.
Math is broken.
Math is broken. Contradiction.
What does it contradict exactly? That it's not constantly 0 in the neighborhood of the point?
It contradicts this.
Okay.
So it's not so much a contradiction. It's if f isn't identically 0, then we get to a contradiction. That means f is identically 0. In a neighborhood of z.
Okay.
Now here's the problem. Here's where it really, so what we've shown so far is we have some region omega, we have some limit point. These zk's are going to z0, and okay, there's some tiny disk. There's some small disk around z0 where f is identically 0. But I don't know anything about f here. How can that one little disk far off in the distance bother me? Why would it bother me? Doesn't seem right that it should, right? What do you think? Maybe it's 0 in this patch. Okay, you got your limit point. It's 0 in that patch, but then it escapes that flat part.
And that turns out to not be possible.
Why? Do you have an intuition as to why that might not be possible?
There should be like, the function can't grow so fast outside of this disk, like in some, like.
It can't grow at all.
Yeah.
Outside of this disk. As much as it may try, it just can't even get started. So think about, my intuition for this is, think about a point like right near there. So there's a disk, and on that disk, the function is analytic. But there's a limit point of zeros on that disk. Like think about a point right on the boundary. So that makes all of this 0. And then and the point here makes all of this 0. Well, why can't these disks converge or something? By the way, of course, I'm assuming that the region is connected.
Because the radius of convergence of each of those disks is the distance to the boundary of at least the distance to the boundary of the region.
That is true. That is true. Let me try to write the word connected in English this time. Connected. But maybe omega is some weird, maybe omega, itself has some pinched region or something. So you start realizing that just how much complex analysis, it looks like analysis, but you're actually doing topology a lot of the time, as we will see. So let's give a topological argument. Ozan, you wanted to say something?
A vague idea. Could you try to look at the biggest open set you can have, look at where it's 0, look at its closure where it's 0, and then extend past that? Because if you're on a point on a boundary, you can like expand around that, and if it's like zero off to, you know, a bit to the left of that point, then that means the series there is zero, and so you can push a bit past that as well. And so there's the biggest open thing is just everything. That's my vague idea, I guess.
Great, great. I like it. I like it. So let's take the set U, which is the set where F is 0. And there might be a boundary to that. And I just want to take the interior of that set. So what we've just shown is that this F being identically 0, it happens on a disk. But anytime you have, you might have other open disks on which that happens. Right? So, so this set where F is identically 0 is open. My claim is that it's also closed. Of course, everything is relative to, in the relative topology of omega. In other words, you take omega and a closed set in R, or C, i.e., U is equal to omega intersect a closed set of C. So that's what it means to be closed relative to omega. Omega itself is open in C, right? You guys have seen these notions of relative topology? If not, I just gave you the definition.
So
and there's a lemma that relative topology is a topology. The open sets and closed sets behave as they would. Okay, why is U also closed? So if I have a limit point, if ZK converge to Z0 and the ZK are in U, then
Z0 is also in the U.
why?
I mean, I would argue in a different way, but
Continuity.
yeah. I would say that U is closed because the complement is open, and then that's from continuity.
So continuity, yes. So continuity means F of Z is equal to 0, but why is it in the interior? But that's what we just proved.
We just
proved that
that.
anytime you have a limit point of zeros, these things, the ZK are all in U. In other words, F vanishes on them. And so this is in the interior by what we just proved. So this is by what we just proved. What was proved. So limit points of U are in U.
But then this disconnects omega, right?
Yes. So if V is the complement, let's do it the way you want to do it. What we just proved is that V is open. And so omega is disjoint union of U and V, both open. But what does it mean to be connected? If a connected set is the disjoint union of two open sets, then
one of them has to be empty, but we showed that.
Yes. But Mitchell, you're not allowed to answer. I want other people. I know you know this stuff. Does everybody remember what that you had a homework about this? Connected implies one of U and V is empty. Of course, this isn't true. If omega's, you could have F be 0 here and 1 here, and here's your limit point. Okay, if it's not connected, then there's nothing to say. Well, you can say that it's on the connected component, 0 on the connected component where you had that limit point. One of U and V is empty. So which one's empty? Come on, all together now. Yeah, okay, everybody's YMCAing. Implies V is empty, which implies U is equal to omega, which implies F is identically 0 on omega. Okay, let's take a step back. We thought we were doing analysis and we started doing topology, right? Let's take a step back. Let me give you a second to finish writing. Some of you are still writing.
Why is Z0 in the interior? I didn't quite follow.
Why is Z0 in the interior of U? So we have a set of limit points. They're converging to Z0. But if F is 0 on all of these points, so F is also 0 on Z0. That doesn't mean it's in the interior. But what was the previous argument? The previous argument was if you had a limit point, then it vanished in a neighborhood.
Okay.
What does that mean? That means it vanishes in a neighborhood of Z0,
Oh, okay.
which means Z0 is in the interior of U.
Okay.
So running that argument again, we ran the argument the first time to get one patch. And then anytime you have some new region, if that new region, whatever the boundary is, you see what it's basically the argument that we're trying to make here. What's the boundary? Anytime you get to a point on the boundary, you get to add a disk. So where's the boundary? There is no boundary. That blob will just expand everywhere and cover all of omega. That's why the function can't get up. You knock the function down once on a limit point, the function can't get up. It's 0. It's just dead. Flat line. Does that make sense?
Is this like sort of like the proof of the?
It's everything about analyticity. If it's analytic, can't get up. Mitchell, you wanted to say something?
I was going to say this sort of like expanding this open neighborhood is like the proof of like or a proof of the Riemann mapping theorem type of.
We're gonna get there. We will get there. Yes. Yes, yes, yes. Schwarz's lemma and all that good stuff. Yes. Does this make sense? Berchin, can you hear me now? Is the internet okay? Yeah? Okay. Kailash, it's good? Michael? Oh, you're muted.
I'm going to have to look at it.
Okay, all right. We can chat offline if you want to talk about it some more. Okay, we have 3 minutes. We can do one. This is like the we said if we have a limit point, then the function 0. So here's an incredible corollary. This is really what people refer to as analytic continuation. Analytic continuation says the following: if you have functions f from omega 1 and g from omega 2, and omega 1 intersect omega 2, these are both open sets, is non-empty, then there exists a unique function f from the union of omega 1 and omega 2, which is holomorphic, and which, if restricted to omega 1, agrees identically with f, and if restricted to omega 2, agrees identically with g. Let's see that again. You have a region omega 1, and f is holomorphic on this region. You have another region, omega 2, and g is holomorphic. If there's any overlap whatsoever, well, they're open, so if there's an overlap, then the overlap is a disk.
So small f and small g should agree in this intersection, right? Otherwise.
Yes, thank you. And thank you. F restricted to the intersection exactly agrees, thank you. Otherwise, it would be a pretty miraculous theorem. There's only one function in all of complex analysis. If f and g agree on the overlap, thank you. If they agree on this overlap, then there's one function. There's only one function. There's a unique function which is defined on both. On the union of those sets. Okay, well, the proof is the proof is immediate. Let's say, so there's obviously one function. Let f be f on omega 1 and g on omega 2 take away omega 1. Just switch the definition. When you switch the definition, that's holomorphic because the place where the switch took place, g is also holomorphic on. So this is holomorphic. Let f1 be any other function which agrees with, let's say, f1 or f on omega 1. Maybe there's some other way to extend. You see, maybe there's some other way. I don't even know what it is. Maybe there's some other function, big F1, which could extend f that way. Then f1 minus f is identically 0 on wherever, on omega 1, on an open set. And if you're 0 on an open set, then there's a limit point of zeros. Which means f1 minus f is identically 0 wherever they're defined. Wherever they're defined. There is one and only one way to extend a holomorphic function, really an analytic function, but holomorphic functions are analytic. There's only one way to extend analytic functions. If you found an extension, it's unique. Okay, this is going to be extremely crucial to all kinds of miraculous things that are coming. Let me just give you a very basic example of this. You see people sometimes writing things like 1 plus 2 plus 4 plus 8 plus 16 and so on is equal to -1. Right? You see like physicists arguing over whether this, what sense, how do you make sense of this? Well, physicists don't need to make sense of it, they just say it. But mathematicians, right? This like, well, what I mean, of course I mean that 1 plus x squared and so on is equal to 1 over 1 minus x. And then I say let x equal to 2. And then here I get this sum. And then here I get 1 over 1 minus 2, which is -1. What's really going on is that there are two functions. This is a function called f. It's defined by the power series. F of x, by definition, is 1 plus x squared and so on. And this function only exists, it has this pole at 1, and it only exists in this region omega 1. Omega 1. There's another function, g, which is defined to be 1 over 1 minus x. And that, so omega 2 is all of c take away 1. And they agree on the overlap. F identically agrees with g on z less than 1. So what people are really saying when they write nonsense like this is they're saying g is the analytic continuation of f. G is the analytic continuation of f. So f at 2 is equal to g at 2. This doesn't make any sense. But if it were to make sense, if you were to make sense of this, this series, which would be the value of f at 2, f is not defined outside of the unit interval. But if you were to make sense of it by analytic continuation, you would give it the value -1. Okay. This is infinity. 1 plus 2 plus 4 plus 8 plus 60. It's infinity. All these pop sci people like to scare people by writing these kinds of formulas. What they mean is the principle of analytic continuation. Okay. There's a new function called g. Forget about f. Ignore f. F doesn't exist anymore. There's a new function called g, and you're welcome to evaluate it at any point except 1. Does that make sense? Okay. That is our time. Any questions?